Let's briefly recall what we did last time. We introduced ordinary differential equations. I think the most important result I want you to be aware of is the uniqueness and existence for nonlinear ordinary differential equations, okay, of this form. And any differential equation of this form with given initial condition has a unique or exists a unique solution if the vector field is ellipses in X and is piecewise continuous with respect to t. In the homework, I ask you to check, to verify, or to search maybe for definitions of ellipses and the local ellipses. Just want to kind of gradually guide you to more formal derivations. And I think that's the main result I want you to be aware of. So after that, we start talking about the linear system, right? That's our main focus. So today we are going to continue our discussion to see how we can derive solutions for the linear systems. I think you know how to derive for certain case of linear ordinary differential equation, but in this class we want to make sure you know how to derive the solution in vector space form. In the state space form, and also using the matrix exponential. Right, we briefly recall what exponential number is, the E number is, and the exponential function can be defined in many equivalent ways, right? This is one way to define exponential function, which is through the Taylor series, okay? So of this form, and this definition of exponential can be generalized to not only real number, but also complex number, right? That's where we have those Euler's formula, right? And also can be defined for matrix. So that's where the matrix exponential is. If you can understand exponential function of complex number, then it should be easy for you to understand or think about exponentials with respect to matrix variables, right? So by definition, the matrix exponential, this one, just think about this as a symbol, right? E to the A is defined as the summation of this infinite number of terms. And this formula is exactly the same as the exponential function, just you use A to replace the real variable X, right? And by this definition, you can compute already matrix exponential, and you see that the right-hand side, well, suppose this series converge, right? The right-hand side is a matrix. If A is an n by n matrix, the right-hand side will be n by n matrix. So the left-hand side, E to the A is a n by n matrix, right? And this power series is well defined for any square matrix. It doesn't matter that what eigenvalues A has. This series is always well defined. To convince you, let's compute it by the definition. All right, let's take a look at this Python 4 code. And I just, this is very simple, right? I just define a function that I can call it my matrix exponential A. What I do is that given any matrix A, I will just have a for loop. I don't want to sum too many terms, right? Just let's say 10 terms should be, 15 terms should be good enough. And what each term is about is just A raised to the power of I divided by I factorial. Okay, since we start from 0, we just have this one. Okay, the first term is identity, and the second term is identity plus A divided by 1, and so on and so forth, right? It's just a plain kind of a summation of the first 20 or 15 terms here. Let's throw out some matrix. Let's say numpy there, mat. 1, 2, 3, 4. Okay, that's my favorite two-dimensional matrices. The return will be E to the A, and then I think the linear algebra SciPy linear algebra package has this exponential M, is the matrix exponential, okay? And that's my, let's say my matrix exponential, right? Okay, let's see how it works. Roughly the same, right? A little bit different. If you add a few terms, let's say 10 terms, will be, I think there will be bigger errors, okay? Okay, let's go back. By this definition, I think there's several properties you have to know, okay? And I think I also understand, right? By this definition, matrix exponential have those and 1, 2, 3, 4, 5 properties, and I think they are very important. Now I'm going to ask you to prove it. Think about how do you prove this one? Let's say proof. Is that easy? Right? By definition. By definition. By definition. E to the A is summation of A, I factorial, I from 0 to infinity, right? That's a shorthand notation. 0 factorial is 1, right? And A raised to the 0 is identity. Let's assume that, then this is the summation form. And if you multiply from the left, E to the A, versus from the right, you can directly from this, so A times this guy. Okay, should be equal to, you can move it out, right? Because A times A equal to A times A, you can change the order, okay? But remember, let's say A times E to the B does not equal to E to the B times A. Okay, the reason you can swap the multiplication is because A times A equal to, well, this doesn't hold if A times B does not equal to B times A, right? This is simple. And the second one is a little bit harder. I will leave that later. For this one, the third property, by definition, let's say A equal to, let's say A is equal to P times D times P inverse. That's called A is what? Therefore, what's the relation between A and D? Okay, A is called similar to D, right? Right. Suppose P is not singular matrix. Okay. By the way, you have to review all the linear algebras. A is called similar to D, and of course, A and D has the same set of eigenvalues. In this case, let's just calculate A. Then we have, first of all, identity, right? Second one is A. A is P, D, P inverse. Okay, the second term. The third term is 2 factorial A what? A squared. A squared is P, D, P inverse times P, D, P inverse. Okay, and dot, dot, dot. I'm not going to, this guy canceled. So this term becomes P, D squared P inverse times, divided by 2 factorial. Right, so following this trend, and we can conclude, hopefully, this is P times E to the D times P inverse. Okay, I already gave you a formal proof for this property. Just by definition, all the proofs are basically start from definition. Okay. All these, let's say, let's call 1, 2, 3, 4, and 5. 1 and 3 are pretty simple. 4 and 5 are both a simple application of property 2. Okay, let's assume that suppose this is the case. Let's accept that, right? AB equal to BA. Whenever AB equal to BA, e to the A times e to the B equal to e to the A plus B. Looks pretty intuitive, but how do you prove it? But let's assume this property is correct. Can you show this? From 2, can you show this one? A times T is a scalar, times A is another matrix, right? This is A times tau. Let's call this the first matrix A1, this is A2. These two can equal to A2, A1, right? No problem, it's a scalar. So it satisfies the condition of property 2. So there was just A1 plus A2, which is A T plus tau. Okay, so that's a simple property. Also from 2, we know e to the A times e to the negative A. We know A times negative A. These two matrices, these two different matrices, right? But they can swap the order. So that also has A plus negative A, which is e to the 0 matrices. As I mentioned, by definition, this is identity. Okay, so that's why e to the A take inverse. You can move that -1 to here. All these symbols looks I think straightforward to you sometimes, but it's just you have to be able to prove them from the basic definition. So all of these two are based upon 2. And how do you prove 2? Is that easy? Yinghan, how do you prove 2? Huh? What's your strategy? If I ask you to show this, do you think it's correct? Yes? Why? Huh? By definition, no. Why it's by definition it's like that? It's true in scalar case, but not, well, it's different in matrix case, all right? Let me show that. Let's see. Next page. Okay. Let's show that here, okay? The proof of 2. Everything should be able to prove, okay? Let's say e to the A plus B. And we know A times B equal to B times A. Equals to summation, let's say, n from 0 to infinity. Let's use this n as the dummy variable for the summation. N factorial, this is A plus B raised to the power n, right? So our goal is to show that this one equal to what? N factorial A times N factorial B, right? That's what we hope. Can you show this? It's pretty hard, by the way. I'm going to give you some key steps. I think that's just make sure you, I think it's nothing to do with matrix exponential anymore. It's just basic algebra and some series. Let's see that this guy should equal to n factorial, a plus b raised to the power n equals to what? It's actually a summation, let's say k from 0 to n choose k, you know that? N choose k terms of a raised to the power k, b times n minus k. This step only holds only when a times b equal to b times a, right? This term equal to this only when a times a, b equal to b times a. That's when you can group terms. Otherwise, they will be different, right? So that's where we use those property or the condition. Okay, if that's the case, I'm not sure whether you can see that this step holds if AB equal to BA, right? Okay, now I'm not sure whether you can see this step, but this equals to let me first give you a property. Okay, let's see a property. Property is n choose the k is n factorial divided by, if you still remember from your high school or middle school, factorial. Okay, Ruben, that's correct. You remember this? Good. Anyway, that's the fact. Keep in mind. Then we can swap this summation. If I want to sum over k first, okay, because n can go from 0 to infinity, k from 0 to n, k is always less than n, right? But n can be infinity, so k can also be infinity, right? So if you swap this, there's some kind of trick there. You swap this, it will be n, let's see, k from 0 to infinity, n equal to k to infinity. All right, n is always bigger than k. So, and if you change that, I think this is equal to a raised to the power k divided by k factorial, n minus k factorial, b raised to the power n minus k. Okay, if you just redefine the variables, I think that's give you the answer here. If you redefine the summation index, because you can call this guy n minus k, call j, right? So that can be factored out. Because you can call this j, then this guy is j factorial. All right, that's roughly this property, and I hope you can remember this. Now I think you can somehow, I hope I convince you that all this number thing can be carried out to this matrix case. The reason we introduced matrix exponential is just because it's a nice way to generalize the scalar ordinary differential equation solution to the matrix form, to the state space form. Okay. Now our goal is to show or derive the solution to this linear system, x dot equal to ax. I call this one autonomous linear system. Hope you still remember what does autonomous mean. And with the initial condition, right? And x belong to Rn is a vector. So by the matrix exponential, this linear differential equation in the vector form has a similar form as the scalar case. Okay, you just need to change the scalar to the matrix, right? And how do we prove this? We basically prove most of the things we introduce. How do we show this is the solution? Okay, good. Vector field. Okay. First, check initial condition. If something is this is a function of t, right? This is a function of t. This guy is a function of t. All the other things are given. A is a constant matrices, right? And x0 is a vector. So this is a function of t. This is a function of t. And this function of t satisfies the differential equation if, first of all, it satisfies the initial condition, right? So you need to plug in t equal to 0 of what is t equal to 0, then what? E to the 0, right? Times x0. E to the 0 is identity. Why? Plug in 0 from the definition, right? Plug in all 0, you get identity. The definition is the identity. So this will be identity times x0 is x0. So it satisfies the initial condition, of course. Now let's check. Check the vector field. What do I mean by that? This guy needs to satisfy this equation, right? So, but I propose xt have this form. So I need to check e to the at x0, take derivative. Let's say it's a function of t, right? I can take derivative. Take derivative should equal to what? I need to check. I don't know yet. I hope it equals to a times what I propose, xt, right? At x0. That's what I want to show, right? This is our objective. We need to show this. Is that the case? Well, we can prove this by definition. Again, by definition, e to the at times x0 equal to what? I times a times t, right? At together is a matrix, right? This is the matrix exponential of a times t, okay? So plus a squared t squared 2 factorial plus a cube t cube 3 factorial dot dot dot, okay, times x0. Okay, we want to take derivatives, right? Now we say, let's take derivative d dt, d dt, right? So that's equal to, do you know how to take derivative? With respect to t, right? T is a scalar. You know how to take derivative with respect to a scalar. So it will be identity take derivative is 0, right? So a times t is a. The homework I gave you some matrix calculus review. I think this, I don't think you need to too much about them. This should be straightforward to you. Then this is the t squared. So this is a squared times what? T squared 2 times t is just t. Okay, the 2 cancel with 2, right? Plus a cube, 3 cancel, this is 2 factorial t squared. Okay, all the way to the future. I'm not sure whether you can summarize this formula with the following equation, that a times identity plus what? At, a raised to the power, that number need to be reduced by 1. So that will be a squared t squared 2 factorial times x0. So which equals to a times e to the at times x0. Okay, satisfies the differential equation. So we can claim this is the solution because existence and uniqueness theorem. Okay, we find one, we check it satisfies, and we know that's the only one that can satisfy this equation, right? So that's our solution, and we prove it. If you take a typical linear system class, they will spend a lot of time talking about this solution to linear differential equations. And we have a brief introduction to this part. Okay. I do the easy one, you do the hard one, right? So in the homework, you need to prove the general case, which is this. The differential equation of the general linear control system has a solution of this form, and that's the homework for you. The last question, right? I think I only ask you to do this, to check this is the solution. Why it doesn't involve any differential equation, so it's easy. Okay. Now the question is that, how do we compute e to the at? It's not e to the a, it's e to the at, it's a function of t. Okay, so this is the solution. This is a differential equation solution. How do we compute or find this solution? Typically, I would say the first case, let's say e to the at. By definition, of course, you can from 0 to infinity, k factorial. This is a t raised to the power k. Given any t, you can compute like this. As I just showed you, it does not have a stable numerical algorithm. I mean, if you just compute like this, it's I don't think it's numerically stable, right? But there are ways to compute them, but it's only for each given t. It's hard for you to obtain a function of t. That's what you want. Okay, I would say it's hard to compute. Okay, I would say for very special case, this series have analytical form. The example I gave you is that maybe the same example I use for defining e to the at, which is 0, 1, 0, 0. That's a nilpotent, so-called nilpotent matrix. And this matrix has the special properties. A raised to the power 2 become all 0. All the future a raised to the power 3, 4, they're all 0. And so you can find it out. It's e to the at. It's identity plus a times t, which is 0, t, 0, 0. Right? At, right? I'm just writing that. And a raised to the power times t becomes 0, because a raised to the power 2 is 0. So all zeros future. So overall you have 1, t, 0, 1. That's an analytical function of e to the at. For any given t, you have a formula, but this is very, very special. I don't think we can do this in general. Another way to compute this or derive the solution, what we want is derive a function, hopefully analytically, okay? A function of t, so that we can analyze the solution of our linear systems. And the other case is using, for diagonalizable matrices, we can use the property 4 or 3, I forgot. property 3, right? Suppose A is diagonalizable. Let me give an example directly. So A equal to 1.5, negative 0.5, negative 0.5, 1.5. It's a very special matrix. In this case, we know, I'll just say, in this case, A equal to, you can diagonalize it. All the matrices are diagonalizable? Of course not, right? Some are not, but all of them are block diagonalizable. So that's a Jordan form. Special case can be diagonalizable. So this one is 1, 1, 1, negative 1. If you trust my calculation, 1, 0, 0, 2 times half, 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 negative half, right? You can check this. I call this guy P, this guy our P inverse. This will be our D. So A is, and the D, what's the relation? Stefan? Similar, okay, they're similar. Okay, so in this case, by our property 3, we know e to the AT, okay, equals to what? P times e to the dt, okay? Suppose this, let's say, let me do this one, okay? AT will be equal to 1, this is t, this is 2t. For any given t, if A can factor like that, this will hold, right? So that will be e to the d times t, P inverse. So which will be P times e to the t, 0, 0, and e to the 2t, P inverse. If a matrix is diagonal, then e to the d will be just all the diagonal entries are just exponential functions. This is because the definition. Okay, you can check this. This will be, I'm not sure whether I mentioned this or not. Did I? Clear from the definition, let's say if, let me make it here, okay? If A is diagonal, let's say if A is lambda 1, lambda 2, 0, 0, then e to the A will be 1, 0, 0, 1, that's identity, right? Plus lambda 1, 0, 0, lambda 2, plus lambda 1 squared factorial, lambda 2 squared factorial, right? So all the diagonal entries, you sum them together, is just the definition of exponential of the scalar lambda. That's the reason, okay? So for diagonal matrices, you can directly move the exponential inside, okay? For non-diagonal, you have to follow this definition. Okay. In this case, if you like, we can further compute it. We'll have some kind of 1 over 2 e to the t plus half 2t, right? I don't have space. You can compute them. That's the first row and the first column. Okay. So you can see the response, let's call this a response map, has exponential raised to power t and 2t. These are called mode of the response. So that depends on the eigenvalue, right? So if this eigenvalue is, let's say, bigger than 0, this is 2, right? This term will grow to infinity. So it's for the eigenvalue, let's say the real part, real eigenvalue is less than 1, less than 0, then they'll be stable. This term will eventually converge. That's why eigenvalue is important for characterizing the system response. Okay, because you know the response is just given by matrix exponential. All right, the last approach I want to mention, okay, is the Laplace transform. I'm not sure whether you still remember. Let's say A equal to A, let's say this is our differential equation with the initial state, let's call it x0, okay, belong to Rn. Laplace transform from your undergraduate signal and system class. Laplace transform is what? Suppose you have a signal. Its Laplace transform is, let's call it x, capital X hat S, from time domain to S domain. In this case, it's a vector. You have certainly learned do you remember the definition of a Laplace transform? Ruben, do you remember that? It's an integral. Let's say x. Let's say xt. dt. I'm not sure whether I remember correctly or not. What I want to remind you is, don't be afraid of vector. Why this one is a vector? Because integral can be defined as a vector. And not only why integral can be defined for vector, because integral is nothing but summation, right? If you sum a few numbers, that's fine. If you sum a few vectors, that will become a vector of the same dimension. Okay, so just think everything in vector is fine, right? If you take derivative, you will have what? In S domain, you will be S times this guy. And also you have an initial state involved, okay? So from this property, this is the basic fact from Laplace transform, then apply, I think you learn solving differential equation using Laplace transform in your undergrad class, but here is just we use everything in a vector form, okay? If you apply the Laplace transform, what you got is, from here, is what? S x at S minus x0, that's the left-hand side, right? Equal to A x S, right? So from time domain, I have an equivalent representation of the differential equation in the S domain. Are you with me? Okay, so that's what? S, this is a vector now, okay? S times identity minus A, then I can group this vector. This is a vector. This is a scalar. Well, this scalar could be a complex number, but it's a scalar. So I can S times I minus A times S equal to initial state, which is x0. So x S equal to Si minus A inverse times the initial state. That's our response in time of frequency domain. And we know Laplace, if you change, you can do inverse Laplace transform of this guy, Si minus A inverse times x0. If you do inverse Laplace transform of this guy, you will find the the time domain solution And we also know from our today's derivation, we also know xt equal to e to the power at x0. Okay, so by this relation, of course, the linear constant can be moved out. So you have e to the at equal to Laplace inverse of si minus a inverse. Okay. That's our conclusion. If you know how to take Laplace transform or inverse Laplace transform, you can also compute e to the at this way. I don't want to go to examples because we don't use this property that much. We just want to make sure that there's different ways to compute e to the at. Okay, that's about it for the computation of e to the at. And I think you just need to remember the definitions and a few properties of matrix exponential, then you're good to go. Why we care about this again, it's because what I'm going to learn, teach you today, next lecture, you will see kinematics is really can be defined in terms of matrix exponential. Okay, I'm not teaching you for you to understand control theory. I'm teaching you this background for you to understand screw axis and robotic kinematics for robot. Okay, if I teach you for control theory, then we will need to do a lot more than what we talked about today. Again, I do the simple case, you do the hard one. So this is your homework. I assume you can accept this is the solution. Yinghan has questions? No? You derive this solution. By what? By definition. Everything can be proved by definition. Okay.